In this video, we learn about recognizing functional groups, where functional groups are common themes of atoms that bond to one another within organic molecules. In organic molecules, we find that carbon and hydrogen are essential, and commonly we also see nitrogen, oxygen, sulfur, and halogen atoms, as well as sometimes phosphorus within the molecule. And we see that those atoms don't bond together randomly, but instead there's certain motifs that we observe where, for example, very commonly within a variety of molecules, including penicillin, we see that an oxygen double bonds to a carbon and that carbon bonds to a nitrogen. We see that a couple different times in this molecule where oxygen double bonded to carbon and that carbon bonds to nitrogen. We see these various themes over and over and over again, and it's important to be able to recognize these themes of atoms that bond together, because by recognizing these so-called functional groups, we can predict the physical properties of molecules, such as their melting point and their boiling point, as well as their chemical properties, meaning what types of reactions these molecules engage in. This has implications for drug development, has implications for nutrition, as we think about things like the melting points and boiling points of fats, and it has a variety of other industrial applications as well. By the end of this video, you'll be comfortable with recognizing and identifying a variety of so-called common functional groups that appear within molecules, including recognizing the name of the functional groups that we see within the molecule penicillin G, a very classic blockbuster antibiotic molecule that revolutionized medicine. The information that you see here can be found in a handout with the module for this chapter on Canvas. Functional groups, as we said, are common themes of atoms that are bonded with one another in organic molecules. There are a huge array of different so-called functional groups. The most common ones are what I have outlined here on this slide. These are the ones that you are responsible for being able to recognize and identify within complex molecules. And it's important to recognize these because if you're looking at a gigantic molecule and you want to draw the reader's attention to a specific portion of that molecule, you could do so by referring them to what functional group you are aiming to describe. Additionally, by looking at and recognizing functional groups, we can predict what types of reactions a molecule will be able to undergo, and we can predict how stable or unstable the molecule will be under certain conditions. For example, if we're thinking about the metabolism of food, ingested orally, passes into the digestive system within the stomach, it's in a very acidic environment, we find that acids are common reactants with a variety of different functional groups. And so if we look at a particular nutrient and we see that has a functional group we would expect to react with acid, we can make a prediction that as that molecule is passing through the gut, that the acid present in the gut is going to play a key role in metabolizing or breaking down that food molecule by carrying out whatever types of reactions are common to that particular functional group. So you should be able to recognize and identify each of these molecules within a complex compound. Let's walk through them. We previously described alkanes, alkenes, and alkynes as so-called hydrocarbons, molecules that have just carbon and hydrogen. If we see these groups as part of a larger molecule, and we want to draw the reader's attention specifically to a carbon-carbon single bond, carbon-carbon double bond, or carbon-carbon triple bond, we can refer to it as an alkane functional group if we're referring to a carbon-carbon single bond, where each of those carbon atoms of that so-called functional group is only bonded directly to other carbons and hydrogens. If we're referring to a carbon-carbon double bond, where the two carbons of the bond are only bonded to other carbons and hydrogens, we refer to it as an alkene. And it's an alkyne if we're referring specifically to a carbon-carbon triple bond, where each of those two carbon atoms of the alkyne functional group are bonded exclusively to other carbons or hydrogens. If there's other atoms bonded there, such as an oxygen or a nitrogen, then it would be a different functional group. So for it to be an alkane, we have to be referring specifically to a carbon-carbon single bond, where the carbons of that single bond are bonded exclusively only to other carbon atoms or hydrogens directly, like we have highlighted here in the upper left corner. In the case of alkenes, the R groups that we refer to there would represent carbons and hydrogens. Same thing with the R groups here in the alkyne example as well. Aromatic molecules, or aromatic functional groups as we will call them here when we're referring just to a subset of atoms within the molecule, refer to the scenario where we have that motif of a 6-atom ring, where there's a pattern of alternating single bond, double bond, all the way around that ring. Now onward to the functional groups that we haven't already talked about in some shape or form in earlier videos. The amine functional group refers to the situation where we have a nitrogen atom, and that nitrogen is directly bonded to these R groups here, where the R groups are carbon or hydrogen. And I'm going to add the addendum here that R, what's directly bonded to that nitrogen, cannot, meaning not equal to sign here, R is not equal to a carbon-oxygen double bond. If the R group there, what the nitrogen is directly bonded to, is a carbon-oxygen double bond, then rather than being an amine group, instead, what we would be looking at is a so-called amide group. And this is a fine scale distinction that a lot of people get kind of confused about as they're starting off their career of identifying functional groups. The amide group is what we would refer to the scenario where you have a nitrogen directly bonded to a carbon, oxygen double bond like so, like I've highlighted in green in the lower right corner of your screen. That would be an amide group versus over here, the so-called amine group with an NE suffix rather than an DE suffix refers specifically to the situation where you have a nitrogen directly bonded to carbons and hydrogens, but none of those carbons are part of a carbon-oxygen double bond. If any of those that are directly bonded to the nitrogen are part of a carbon-oxygen double bond, it makes the group called an amide instead. And the distinction is important because these two groups react very, very differently. We will find that the amide group is present in all proteins, and that makes it very biologically relevant. And later on, we will learn about some of the reactions of amides that are biologically relevant. Carrying on with our functional group identification, we have alcohols, and alcohols are going to refer to molecules where we have an OH group, like so, directly bonded to a carbon, and I should note that that particular carbon atom cannot be a carbon-oxygen double bond. If that was a carbon-oxygen double bond that is directly connected there, instead of being an alcohol, the group would instead be a carboxylic acid. Because you see, in carboxylic acids, we have an OH group directly bonded to a carbon, just like an alcohol has an OH group directly bonded to a carbon. But in the case of the carboxylic acid, the OH group that's bonded to a carbon, that carbon is double bonded to an oxygen atom. And so that is going to distinguish a carboxylic acid from an alcohol. The group can either be an alcohol or a carboxylic acid. That OH group can't be part of both groups. So it's an alcohol group if it's bonded to a carbon that's not a CO double bond. It's a carboxylic acid if it's an OH group bonded to a C double bonded to an O. So it's very, very much about pattern recognition here to distinguish between the different types of functional groups. Likewise, an ether, right here, is an oxygen sandwiched between two carbon atoms. And in the case of this, much like the case of the alcohol, the carbons that are bonded there cannot be C double bonded to O. If they are, then, or if one of them is, I should say, then the functional group that you would be dealing with would be a so-called ester down here, where the ester, you'll notice, has a carbon single bonded to an oxygen, much like an ether, single bonded to another carbon, and that carbon is part of a carbon-oxygen double bond there. So the distinction between an ether, E-T-H-E-R, and an ester, E-S-T-E-R, is this seemingly subtle difference where rather than having carbon, oxygen, carbon, we have carbon, oxygen, carbon double bonded to an oxygen here, making the distinction between these two different functional groups. And the reason we distinguish between the two is they have very, very different reactive properties and very different functions that they are used for. Esters are commonly used as flavors and fragrances. Ethers, very, very infrequently, are used as flavors and fragrances. Alkyl halides are structures where we have a carbon directly bonded to a halogen atom. So we refer to those as alkyl halides. Thiols are molecules that have notoriously strong, nasty smells, such as the smell emitted by a skunk is due to its production of molecules that have thiol functional groups. And a thiol functional group absolutely has to have a sulfur that is connected directly to a hydrogen, and then that sulfur is also connected to a carbon. That's what makes a so-called thiol group. On down the line here, aldehyde groups are common and important biologically. Aldehyde groups are known as structures that have a hydrogen atom that's bonded to a carbon. That carbon is part of a CO double bond. And then off to the other side, this R group here represents carbon and or hydrogen there. Ketone is related to an aldehyde but distinct in that a ketone has a carbon-oxygen double bond that's directly bonded to two carbon atoms. So in the case of an aldehyde has a carbon-oxygen double bond that's bonded to a hydrogen on one side and carbon or hydrogen on the other. Ketone has to have a carbon on both sides here in order for that to be described as a ketone. So that wraps up this comprehensive list of functional groups that you are expected to be proficient with for purposes of this class. Let's apply this information toward an example problem. We are going to go back and return to our penicillin molecule for this example. So I've brought in the structure of penicillin G, one of a variety of different derivatives or closely related structures to the original penicillin, where what we aim to do in this penicillin structure that we see here is to identify all of the functional groups that we can based on the list that we learned here in the upper left-hand corner. So taking a look at how we go about doing that, we will look for common motifs that we see within the structure, and usually for complex molecules that are non-hydrocarbons, meaning molecules that have atoms other than just carbons and hydrogens, meaning that have something other than alkane, alkene, and alkyne groups. Usually we don't bother listing the alkane group. All of the other groups here we generally list, but alkanes we typically disregard if there's other functional groups present, because the alkane we kind of think of as just the basic skeleton of the molecule, and there's in most organic molecules at least one carbon-carbon single bond somewhere that would count as an alkane, so we generally kind of ignore that, based if only on the fact that it's so ubiquitous. So let's focus on these other functional groups here and try to see what we can come up with. So taking a look at them, we're going to circle the different functional groups that we find here. I see this ring that we previously recognized as an aromatic group, so I'm going to label that as aromatic. Aromatic, remember, refers specifically to that six-membered ring with alternating single bonds and double bonds. Now, coming to other parts of this, what I generally look for are carbon-carbon double bonds, carbon-carbon triple bonds, representing alkanes and alkynes respectively, and then I look for heteroatoms, that is non-carbon, non-hydrogen atoms, to help guide myself toward the functional groups that are present. And indeed, I see here an oxygen atom that's bonded to a carbon. So I start to think about what pattern that would follow. And to see what pattern that would follow, we can narrow down, based on the fact that we have a carbon-oxygen double bond, we can narrow down to several of the different functional groups that we have here. Namely, we can narrow down to ketones, esters, carboxylic acids, amides, aldehydes, And that's about it. So it's got to be one of the ones on the bottom row here if we've learned this functional group. So in the case where we have an oxygen double bonded to a carbon, where do we go from there? Well, we go over to the nitrogen. And do we have anything here that has a carbon-oxygen double bond that's bonded to a nitrogen? We do. It's the amide group. So I can go ahead and fill in the rest of my circle with representing that a nitrogen atom bonded directly to a carbon-oxygen double bond is going to allow this to be referred to as a so-called amide group. And you could include this other carbon over here if you want. You don't really have to. What absolutely has to be present for it to be referred to as an amide is asked to have that carbon-oxygen double bond directly bonded to a nitrogen. That is represented and referred to as an amide group. Do not try to also label this as an amine group. The nitrogen, instead, is directly bonded to a carbon-oxygen double bond, which means that it cannot be an amine group. It's a common mistake that people make, and that's why I'm harping on it. Likewise, if we come over here, we have another carbon-oxygen double bond, and even though this is part of a ring, in that ring it's bonded to a nitrogen, so that still makes it an amide group. What if we come over here? We have a carbon-oxygen double bond. That allows us to narrow down the possibilities to everything in this bottom row here. We see what theme it fits. We have a carbon-oxygen double bond, and that carbon is directly bonded to an OH group. So that would make this a carboxylic acid. So I'm going to go ahead and finish off circling here, and I'm going to label that Ca for carboxylic acid. And then last but not least, we see a heteroatom over here. That's a sulfur atom. And we look for sulfurs within our chart here. The only sulfur I see is a thiol, and our thiol group shows specifically we have a sulfur directly bonded to a hydrogen. Since in this case we have a sulfur that's not directly bonded to a hydrogen, we can't label that a thiol. Instead, this is some functional group that we haven't learned within our functional group lineup. So you would not be held responsible for that particular functional group. Instead, what you should be able to recognize and label would be all the functional groups that I've shown here that correspond to the ones you are expected to know for purposes of this class. If you were to take a more advanced organic chemistry class, you would get into some additional complex functional groups, but for purposes here as in survey class, this is what you are expected to know. And again, there is a handout on Canvas for this module that has all of these printed out like so.